So today we're going to talk about something absolutely fundamental to how AI works. It's memory. We are seeing a massive shift right now, moving away from a world of just exact keyword searches and into a totally new era. An era where computers can actually understand the meaning behind our words. And I'm telling you, this isn't just some small tweak, it's a giant leap. And really getting your head around it is essential for anyone building or investing in or even just trying to understand AI today.
Okay, let's dive right in. First, we're going to start with the basics, the timeless rules of data that, believe it or not, still run the show even for the most advanced AI. Then we'll uncover what I call the golden rule for storing the huge files these systems need. After that, we get to the really cool part, how AI takes our messy, human language and translates it into the clean, predictable world of math. We'll then look at how that completely changes the game for search, and finally, we'll see how all of this comes together to give an AI what's basically an open book exam, a technique that makes it smarter, safer, and way more useful in the real world.
All right, first things first. Before we get into all the futuristic AI stuff, we've got to ground ourselves in the principles that make any software reliable. You know, AI is revolutionary, it's exciting, but it doesn't just float in a vacuum. Nope, it's built right on top of a foundation of data management that's been proven solid over decades of computer science.
And it doesn't matter how smart our systems get, we still need a core safety net to make sure our data is trustworthy. That safety net is the ACID principles. Look, for any serious application, these aren't just nice-to-haves, they are totally non-negotiable. It's the promise a database makes to you that says, hey, your data won't get messed up or just disappear.
So the first big idea here is persistence. The easiest way to think about it is as a computer's long-term memory. See, any running app uses super fast RAM, but that memory is like a fleeting thought. The second you close the app or the power goes out, poof, it's all gone. Persistence is the act of saving that data to something permanent, like a hard drive. It stops the software from getting amnesia every single time it restarts. It's really our main defense against crashes or power failures. Without it, every app would be stuck just forgetting everything it ever did, over and over again.
And this is that safety net I was talking about, ACID. Let's just do a quick flyby. Atomicity means a transaction is all or nothing. Think of a bank transfer. You can't have money leave one account if it doesn't arrive in the other. Consistency makes sure that only valid data gets saved. Isolation keeps different operations from tripping over each other and making a big mess. And finally, durability is the ultimate promise. Once the system says your data is saved, it is saved, period. These 4 rules are the bedrock of trust for any data system, whether it's a simple website or a global AI.
Okay, so we've got our foundation set. Now let's talk about the first huge problem that AI throws at this traditional way of thinking. AI models are, well, they're data monsters. They need massive data sets. We're talking HD videos, whole libraries of books, millions of pictures. And our first gut instinct on where to put all this stuff, it's usually completely wrong.
Yeah, the old way, the intuitive way, was to just cram these giant files, they're called blobs for binary large objects, right into our database. You know, just stick them right next to our normal data, like usernames and purchase histories. I mean, it seems simple, right? Keep it all in one place. But what you're really doing is setting a ticking time bomb for your system's performance, its cost, and its ability to grow.
And this isn't some abstract theory. You will eventually smack right into a hard, unmovable wall. For example, the popular NoSQL database MongoDB has a strict 16 megabyte limit for a single document. I mean, that's not even enough for a handful of photos from your phone, let alone a short video or a serious AI training file. And this isn't just a MongoDB thing. It's a universal truth about how databases are designed. They're built for fast, structured queries, not to be a dumping ground for giant files.
And that brings us to what is maybe the single most important rule for building AI systems that can actually scale. This is the golden rule. It's so important I want you to just burn it into your brain. Stop putting huge binary files in your database. Trying to do it doesn't just make your system slow and expensive, it pretty much guarantees it will fail once you hit those limits.
So what's the right way to do it? Well, the modern solution is this hybrid strategy. It's actually really simple and super effective. You keep all the small, lightweight, searchable stuff, the metadata, in your database. This is things like file names, dates, user IDs, and this is the key part, just a simple pointer to where the big file actually lives. And the big file itself? You put that in a dedicated cloud storage service like Amazon S3 or Azure Blob. These things are designed from the ground up to store practically infinite amounts of data cheaply. And boom! You get the best of both worlds, a lightning-fast database and a limitless digital warehouse for your AI's data.
All right, so now we know where to store our data. Let's get into the really mind-bending part. What are we storing, And how on earth does an AI even understand it? This is where we pull back the curtain and reveal the secret language of AI. And trust me, it's not what you think it is.
This slide right here, this is the single most important concept to really internalize if you want to understand modern AI. We talk to it with words, right? We type in English, it gives us English back. But under the hood, the AI doesn't see cat or dog or love. It just sees numbers. It doesn't process language at all. It processes high-dimensional math. Every word, every sentence, every single idea gets converted into a string of numbers.
And these numerical representations have a name. They're called embeddings. And we really need to pause here for a second because this is the critical point. An embedding is basically a list of numbers, a vector, that acts like a set of GPS coordinates. But instead of mapping a physical place on a map, it's mapping the location of a concept in this giant, abstract space of meaning. In this space, ideas that mean similar things, like happy and joyful, are placed really close together, and concepts that are totally unrelated, like happy and diesel engine, are super far apart. We are literally turning the messy, beautiful chaos of human language into a structured mathematical map.
And here's where it gets amazing. Because these concepts are now just numbers, we can actually do math with them. Let's walk through this famous example. You can take the vector, the list of numbers, for king. Then you can mathematically subtract the vector for man, and then add the vector for woman. And the resulting point in this meaning space lands incredibly close to the already existing vector for queen. I mean, just let that sink in for a second. We are doing algebra with ideas. This is the magic of embeddings. It's how an AI starts to figure out relationships it was never explicitly told about.
If the whole GPS thing isn't clicking, let's try another analogy. Imagine a library of flavors. In a normal library, you'd find honey under H and sugar under S, miles apart. But in this new library, we'd organize them by how they're related conceptually. Honey, sugar, and maple syrup would all be right next to each other in the sweet section because they feel similar. That is exactly what an embedding space does for our ideas.
Okay, so this leads to a really interesting new problem. If our library is organized by flavor instead of by the alphabet, well, how do we find anything? We can't just look up an exact word anymore, right? This completely new way of storing information demands a completely new way of searching for it.
So let's just ask the question directly. If all our text is now just coordinates on a giant map of meaning, how do we search it? You can't just type in a keyword and look for a perfect match. Instead, you have to ask the system to find concepts that are near your query. You're not looking for a specific word anymore, you're exploring a whole neighborhood of related ideas.
And this slide just nails the difference. A traditional SQL search, the kind that's powered pretty much everything for 50 years, is basically like hitting Control F in a document. It's looking for the exact sequence of letters you typed. If you spell it wrong or use a synonym, you get nothing. Vector similarity search, on the other hand, is all about finding things that are semantically close. You could search for ideas for a trip in a hot place, and it could bring back documents about beach vacations or tropical getaways, even if your exact words aren't in there at all.
This table breaks it down perfectly. With a SQL database, your queries are strict, they're logical, find records where the status is exactly equal to the word active. But with a vector database like Chroma, the query is conceptual. Find concepts that are near the idea of summer vacation ideas. The whole point is different. We're moving from just retrieving structured data to actually discovering information based on what it means.
So now that we have this powerful new way to search by meaning, we can finally put all the pieces together. The hybrid storage, the embeddings, the vector search, and create this incredible technique called Retrieval Augmented Generation, or RAG for short. This right here is the key to building AI systems that are practical, reliable, and actually up to date.
So what even is RAG? Well, at its core, it's a really clever shortcut. Training a giant model like GPT-4 costs millions of dollars and takes months. It's totally impossible to just retrain it every single day as new information comes out. So RAG gives us a much cheaper and more reliable way to do things. The best way to think about it is like this. You're giving the AI an open book exam instead of forcing it to memorize the entire internet.
And here's how that open book exam works, in 4 pretty simple steps. First, you ask a question about something the AI couldn't possibly know. Maybe it's too new, or it's your company's private data. Step 2, instead of just guessing, the system takes your question, turns it into an embedding, and searches that vector database we talked about. Step 3, the database finds the most relevant little snippets of text, these are the notes for the exam, and sends them back. And finally, the AI gets the original question plus this new relevant context,
and is told, okay, now generate an answer. This process slashes the number of times an AI hallucinates or just makes stuff up.
Here is a perfect, real-world example. Imagine you ask your AI, how do I reset the screen on my brand new 2024 car? Well, the problem is, the AI was trained on data from 2023. It has never even heard of this car. It has zero knowledge of it. Without RAG, it would probably just say, I don't know, or worse, it would make something up. But with RAG, the system first queries a vector database that you've filled with the 2024 user manuals. It finds the exact paragraph with the reset instructions, and it hands that little piece of truth to the AI. And then, the AI can generate a perfect, accurate, step-by-step answer. It's a truly brilliant and practical solution.
And all this brings us to one final big idea to chew on. We've gone from the super rigid rules of ACID all the way to this fluid, mathematical world of meaning. We're now building systems that care more about how concepts relate to each other than about exact spelling. So the question I want to leave you with is this. How is our very definition of reliable data going to change when our smartest systems care more about how an idea feels than how it's spelled? This is a huge shift in computing, and we are just getting started. Thanks for tuning into this explainer.